let me write this here. So lambda n plus n goes to p, total rate of neutron getting converted to proton is a times integral from minus infinity to infinity, with the understanding that mod q plus q should be larger than AB. Okay, so that this square root is the square root of a positive number. And let me remind you that when I am talking about mu nu, it's the electron neutrino. Okay, because the muon and the tau neutrinos are separately concept. They are not going to play any role in this analysis. Is this okay so far? Okay, so now we have to also consider the reverse process, right? Because after all, if you are trying to use these rates to try to understand how the number of neutrons change as a function of time, right? We have to take into account the fact that the neutrons can get converted to protons, but protons can also get converted to neutrons, right? So by exactly the same kind of calculation, we have to calculate the rate for lambda p to n. Okay. And again, this gets contribution from two different sources, three different sources, because all the three processes that we saw, its reverse process, could happen, right? So you have to take into account all those processes. And basically, the result that one finds is similar to this. Okay? The fact that there is the same A that is appearing shouldn't be surprising, because after all, it's the same matrix element, right? You are just by CPT conjugation, it's the same matrix element that will appear. But of course, some factors will be somewhat different.
But sir, here, like the neutron decay process, if you see from the opposite side, there is three particles which are colliding and producing a neutron. So in that case, really the analysis whatever we have done, like the sigma is basically one of the particles cross section and the other one is hitting. So how we can think for this?
Well, now you have to calculate the probability that the three particles come together, right? Which can happen because you are considering thermal density, right? If you are actually doing a scattering, right, then the probability that the three particles are coming together is zero, because you are calculating particle per volume, right? But in a thermal bath, right, it can happen that three particles can come together, right? It's just going to be proportional to the densities, right? If the density of particle is sufficiently big, they can come together.
Is this analogy of this cross section to be a small disk kind of thing? This will not hold for the three particle, right?
Well, it will hold in the sense that you have to have the disks overlapping between two particles, right? The disks have to be together. Right? So that's how you have to draw the analogy. Right? It's true that one single particle collision will not do it, right? But you have to have the overlapping disks, and then they can do it. We'll see that factor. So q squared, q plus q squared over 1 plus basically what will happen, the change, net change is that these signs get reversed. So for the reverse process, as you are saying, that when three particles come together, right, electron, neutrino and proton come together to produce neutron, right, that for that process, these are both the occupancy numbers. You are taking the product of the occupancy number for the electron and for the neutrino, right, or the antineutrino, right, because electron, antineutrino has to come together with to the proton, right. So the probability for that happening will be proportional to the densities of both electron and antineutrino. They are both in the initial state.
So here key is just E or minus.
Pardon?
So in this case key is just E or E minus E.
T. T is the temperature of the
Small q.
small q is the same. Oh, small q. Small q,
Minus E.
yeah, is basically the. Yeah. So in this case, the small q will be the energy of the antineutrino. That's why this sign is reversed. So if at xn, if xn is the fraction of antineutrons, the fraction of neutrons, which means nn over nn plus np, right? The fraction of the baryons that exist as neutrons. Then 1 minus xn is the fraction of protons, right? np over nn plus np. And then the equation that tells us how xn evolves as a function of time is dxn dt equal to minus lambda n to p times xn plus lambda p to n times 1 minus xn. Right? So this is the equation we'll be using to study the evolution of the number of neutrons as a function of time. But before we do that, let's first check what happens in the equilibrium situation. That for t much larger than MeV, we expect the system is in equilibrium. We expect equilibrium. Okay. So in this case also we have T nu equal to T. And we should have dx and dt equal to 0. Instantaneously. That's the definition of equilibrium, right? That you shouldn't have the number of neutrons shouldn't change as a function of time. Okay, except for the fact that the T itself is changing, so that may cause some change. But suppose it's at a fixed temperature, right? Assuming T constant. Okay, so let's ignore the expansion of the universe. Okay, assume that we have a gas of neutrons and protons with constant T. Okay, forgetting about the expansion for now. So this will tell us that Xn over 1 minus Xn, that's the ratio of neutrons to protons, Nn over Np, should be equal to lambda P goes to N divided by lambda N goes to P. Is this clear? So let's try to calculate this. Lambda N goes to P, and I'm setting T nu equal to T. I want to calculate the ratio of these two, right? Okay. But at T nu equal to T, because I have set in equilibrium T nu and T are the same. Okay, T nu equal to T. So this gives you A times integral minus infinity to infinity dq 1 minus m square over q plus q whole square to the power half. So what I'm going to do now is I'll try to make this look like this. Okay, so how to do that? We just take out this factor, the common factor. Okay, so we write this as e to the power q plus q over t minus mu e over t plus 1 times e to the power minus q plus q over t plus mu e over t. Is clear? Right, I have just taken out this factor and written like this. Similarly, from here, I'll take out this factor, so it looks like this. Times e to the power q over t, I'm setting t nu equal to t minus mu nu over t times e to the power q over t Is this clear? Just simple manipulation of this expression. But now you see that in this product, so what is the difference between P goes to N and N goes to P? Is this product, right? Right? Everything else is same. So in this product, this minus Q over T and plus Q over T cancel. Right? Everything else is Q independent. So you can take this outside. So you can write this as e to the power q by t, it's going in the numerator, minus mu e over t plus mu nu over t times lambda p goes to n. So now let's substitute here. Lambda p goes to n divided by lambda n goes to p. So you basically get inverse of this. So this is e to the power minus q by t plus mu e over t minus mu e over t. So do you recognize this formula? Nn over np. So where did this come? Yeah, yesterday we calculated Nn over np assuming thermal equilibrium, right? Right? Equilibrium gas of neutrons and protons, right? We calculated Nn over np and we got exactly this number. So it's of course not a surprise, right? Because in equilibrium, dx and dt shouldn't change. Right? But they're just saying that at least whatever you have done things consistently. Right? That demanding dx and dt equal to 0, if you calculate Nn over np, we get exactly what we got yesterday. Okay, and we have of course assumed in this whole analysis that neutrons and protons are non-relativistic, so that their kinetic energy to the contribution to the kinetic energy is small. Right? Here you have assumed it in writing this energy balance, right? In doing all this, you have been assuming that the energy of neutrons and protons are just Mn and Mp. Okay, which is of course true if they are non-relativistic. Right? And this formula that we have written here was also derived assuming that they are non-relativistic, right? Because we expanded this square root of Mn square plus k square as Mn plus k square over 2Mn, right? And similarly for the proton. Questions?
So can you repeat the last this statement?
This one? So lambda n goes to p, right? This was the expression that I had written down. Right? Now the point is I got this expression for Nn over Np, right? By demanding that dx and dt equal to 0. So I have to calculate the ratio of the two. Right? So lambda n goes to p, I try to rewrite in a way so that it looks like lambda p goes to n. And as I had said, the only difference is in these two factors, right? In the two expressions. So I want to make these two factors that appear here, these two factors, look like these. Okay? So I just pulled out these factors. This is just algebraic. I mean, this is identically equal to this, right? I just pulled out these two factors, right? And of course set nu equal to t. Okay? And after I have pulled this out, right? Important point is that the q dependence cancels. Because if the q dependence didn't cancel, then of course it will not be a multiplicative factor outside the integral, right? But because the q dependence cancels, I can just think of this as a multiplicative factor outside the integral. Okay? And that's how I wrote this as this times lambda p goes to n. Okay? And then substituting this in this formula, I got the ratio of neutrons to protons in equilibrium to be this. And this is exactly the statistical formula that we had found yesterday. No, that doesn't. It's not. Okay. It's not saying this isn't. I mean, quite like that. But we'll see what it means, right? When the neutrinos, when this ceases to be in chemical equilibrium, right? Because this formula will fail eventually.
Is lambda a function of time?
Yes, everything of course is a function of time, right? But for this calculation, right, I forgot about the evolution of the universe. Right? I just assume that let's suppose that you have protons and neutrons at some particular temperature. Right? And there, I assume the neutron temperature is the same as the proton temperature, right? So under that approximation, of course, we have established equilibrium, right? If nu and t are the same, right? That means the system is in equilibrium. So dx and dt should be 0. Okay. And by demanding dx and dt equal to 0, you got the Nn over Np ratio. Right. And this ratio is exactly what we had derived last time from the thermal equilibrium condition.
But so what are the parameters that are dependent on time in this integral? Because Q is integrated out.
Oh, because T is depending on time, right? T and T nu are both time dependent. Right? So because of this, lambda will be time dependent. Yeah, and that's important because eventually, how do you decide when the system falls out of equilibrium, right? When this reaction rate becomes slower than the expansion rate, right? Then the system will fall out of equilibrium, right? And then we cannot use this formula anymore, right? To calculate the ratio of xn to 1 minus xn, you have to actually solve this equation, right? dxn dt equal to this. You have to solve this and evolve it, and that will be a coupled equation that takes into account the evolution of xn as well as the evolution of the temperature. So here it looks like that if T nu is equal to T, everything is in thermal equilibrium, right? But that's because you have ignored the fact that T actually is a function of time, the temperature, right? Once the temperature becomes a function of time, right, then this is a coupled equation for xn as well as T, which you have to solve. Other questions? Okay, so let's now try to determine at what time this reaction rate becomes slower than the expansion rate, because that's when the thermal equilibrium stops, right? And you have to start using this detailed evolution equation. So to get a crude estimate, so let's estimate lambda into P at T of order MeV. And at that temperature, to get a crude estimate, we will just ignore these Q over T and mu over T, right? So these are order 1 numbers. Q is of order MeV, right? So Q over T is of order 1, mu over T of course is small, right? So let's just ignore this and just try to get a rough estimate. So this becomes roughly A times integral minus infinity to infinity dq, and we'll also ignore this me over q plus q factor because this is again of order 1. Okay, so just drop this and do the full integral from minus infinity to infinity. Okay, again as an order of magnitude estimate it doesn't matter. So you get q square, q plus q square. In fact, let's just ignore the capital Q from here because q is going to be of order MeV anyway. 1 plus e to the minus q by t, 1 plus e to the q by t. Okay, so roughly this is the number. Okay, very crude estimate, right? Up to order 1 factors. Is this okay? Right? I'm just making drastic approximation, but if you are just going to trying to get an estimate, it doesn't matter, right? As long as you are not setting large numbers to 0 or large numbers to 1, you are okay. Right? Order 1 numbers can always be set equal to 1. Right? And these numbers are all order 1. Right? Q over T is order 1, mu over T is 0, and Q on Q, capital Q of the same order, right? Because at temperature T, the neutrinos will have high energy, right? At least of the order T, which is of order MeV. So this integral can be done, and this gives you something like 7a t to the 5 times a numerical number that turns out to be 7 pi to the 4 over 15. The fact that it goes as t to the 5 is easy to see, right? Just set q over t equal to u. Right? That will give you t to the 5. Right? And this number is just the integral. You can put it in mathematics and do this integral, you will find this number.
So here, in writing this equation,
Yeah, exactly. So because q plus q, right? Q is of order MeV. Small q you expect to be of order MeV, right? Because you have the temperature that you're considering is of order MeV. So this ratio is of order 1. ME is 0.5 MeV, right? So you just set this of order 1, right? And do this full integral, right? You even ignore the fact that you have some excluded ratio. You can also calculate H, which you have done before. H is square root 8 pi g over 3, and then we had half AB t to the 4 times 43 over 4. At 1 MeV, the degrees of freedom count gave 43 over 4, if you remember. So this is some number times t square, right? It's proportional to t square. And once you put the numbers, I'll leave it as an exercise to check that once you put the numbers, that lambda n to p divided by h, this ratio, this is the reaction rate versus the expansion rate. This ratio goes as about a second. Sorry, here there's no second. This reaction rate goes basically as T over MEV cube. Okay, you have to know the value of A, of course, right, which you wrote down yesterday. So what this is telling us is that when T is much larger than MEV, then the system is in equilibrium because the reaction rate is much faster than the expansion rate. If, on the other hand, T is much less than the MEV, then the system is out of equilibrium because the reaction rate is smaller than the expansion rate. So, in that case, you cannot use thermodynamics anymore to calculate the fraction of neutrons. You have to actually solve this set of equations to find a fraction of neutrons, to calculate Xn. Is this clear? So let's look at this equation again. The right hand side of the equation involves these rates. And what do these depend on? These rates, if you look at the expression, they depend on T, mu E, and mu nu. Right? Others are also universal constant. The constant A is some thing that depends on the weak interaction strength, right? Those are universal. But the expressions for lambda had these three parameters. And T nu. Sorry, I should have T nu. These we had already calculated. T and T nu. Right? We gave this detailed analysis giving how T and T nu evolves as a function of time. So if these things had not been there, then it's a very simple set of equations, right? Equation in one variable, dx and dt, right hand side is completely known as a function of xn, right? So you just integrate it. numerically. So what we will now try to argue is that this mu e and mu nu, okay, for the range that we will be interested in, they can be set to 0. Okay, so that you can actually evolve this just as a single variable equation. Okay? Otherwise, you have to keep track of how these things are evolving as a function of time. Pardon? T and T nu are not the same, but we know exactly how they change as a function of time, right? Because I had also written down a table, right? T and T nu, how they are changing as a function of time. So they are not the same, but you know exactly how their time dependence is. Right? So that's what you have to put in when you try to numerically integrate this equation.
So the only unknown part is the mu
Mu
e and
e and mu nu, right? Which I have not said earlier, right? How to determine the time evolution, but we will now try to argue that in the range that we are interested in, both can be set to 0.
But if mu over t is constant,
Yes.
then for the time dependence of t, it's like the mu e time dependence also.
But mu e over t is not constant. That's the point, right? Mu nu over t is constant because it's relativistic.
Oh, okay.
But mu e over t, e becomes non-relativistic during this transition, right? So it's not constant.
So we are left with only mu.
We'll be left with only mu e. But let's try to go through the mu nu argument once more. Okay? But we'll be essentially left with only mu e. Okay. So let's recall how to determine this. Right? What is the philosophy for determining these objects? Mu e and mu nu. Okay, then we'll try to see if they're smaller big. Okay. So we have the expressions for n e minus plus, and that's given by 1 over 2 pi square times 2 integral 0 to infinity dk k square right? This is the number density of E minus and E plus, right? For E minus it's minus mu e, for E plus it's plus mu e. That's the difference. Similarly, n of nu and nu bar will be 1 over 2 pi square integral 0 to infinity dk k square. This time you can ignore the mass. E to the power minus k minus plus mu nu over t over 1 plus e to the minus k minus plus mu nu over t.
So here you are assuming they are in thermal equilibrium.
Well, E is in thermal equilibrium because E is with gamma. Right? Here I should use T nu. Even if they are not in thermal equilibrium, right? We saw that their distribution, right, is as if they are in thermal equilibrium, even after decoupling, right? Because mu nu and T nu both falls as 1 over 8. So that's the mu nu and T nu that we have to use.
And sir, here the 2 is not here because only one type of
Exactly. That's it. Yeah. So these are of course formulae. Now what determines them? So the mu e is supposed to be determined from this formula. Ne plus minus Ne minus plus Np minus Np bar equal to 0. This is the condition that the total charge is 0. Right? E plus P minus and P bar are the only charge carrying particles at this time, right? So the charge, so of course the charge is conserved, but not only the charge is conserved, we know that total charge in the universe is 0, total charge density, right? So you say this equal to 0. The other is lepton number, Ne minus Ne plus N nu minus N nu bar divided by N gamma is small, right, of order 10 to the minus 9. Okay. So this one is telling you what? So this one is telling you that Np minus Np bar, Np bar is 0. At this temperature, we have seen earlier that Np bar you can just ignore, right? Roughly Np. Now Np, we don't know, Np is not fixed at once, because what is fixed is Np plus Nl. That's the number of baryons. Okay? But in principle, you know Np because of these equations. Right? As you evolve these equations, it tells you what fraction is neutron and what fraction is proton. Right? So because you already know Nb over N gamma, right, we can calculate Np over N gamma as a function of time using this. Okay? And if you have to evaluate mu e, actually mu as a function of time, that's the number you have to use to substitute here. Ne plus minus Ne minus, it will give you Np in terms of Np minus Np bar, that will read out from there, right? And then substitute here to solve for mu e. Yeah, that's the strategy for finding mu e, right, if you have to find it. Mu nu, similarly, once you have found Ne minus minus Ne plus, right, from this, okay, you substitute in this equation, assume that this is known, some 10 to the order 10 to the minus 9, and you can calculate Nu minus Nu bar. Okay. That Nu minus Nu bar, you substitute, you use this equation to find mu nu. Okay. That's the most general strategy. Right? You have to solve a coupled system of all these equations, right? Xn, mu e and mu nu. But as I said, what we will try to show is that mu e and mu nu can be set to 0, okay, to a very good approximation, okay, in the range that we are interested in. So let's start from mu nu. Okay, this argument we have gone through many times, but let me go through once more. So if you look at this formula, Nu minus Nu bar. What is the difference between Nu minus Nu bar? One has mu nu over T nu, the other one has minus mu nu over T nu, right? That's the only difference. But we know that Nu minus, from this, we can read out Nu minus Nu bar from here, right? Because we can calculate this in terms of this. But this over N gamma, we know is going to be of order 10 to the minus 9. Why? Because after all, number of baryons, baryon to photon ratio is 10 to the minus 9, right? So proton to photon ratio is also going to be of the same order, right? Because you have this fraction of 1 minus xn, right? That's the order 1 number, right? But proton to photon ratio will also be of the same order, right? 10 to the minus 9. So from that it tells us that this to N gamma is 10 to the minus 9, and hence this to N gamma is also 10 to the minus 9. Right? So this is 10 to the minus 9.
Could you repeat?
Repeat
Yes.
this one. Okay. So let's go through one by one. So we cannot do anything with these equations unless you know Np minus Np bar, right? But Np minus Np bar is known from there, right? Np minus Np bar at this temperature is nearly equal to Np because Np bar is small. Okay. And that is 1 minus xn times Nb. Right? So Np minus Np bar over N gamma is of order Nb over N gamma, because 1 minus xn is a number of order 1, which is 10 to the minus 9. This tells us that Ne plus minus NE minus is of order 10 to the minus 9 over N gamma. And that also tells us that Nu minus Nu bar over N gamma, that's from the second equation. Right? Once this over N gamma is of order 10 to the minus 9, you take it to the other side. So this over N gamma is also 10 to the minus 9. Is this clear? Let me erase this now to make some space. Later on I'll put it back.
So, writing this last step,
Yes?
there this assumption goes in, right? That NL over N gamma plus
Yes, this assumption goes in because this part is an assumption, right? NL over N gamma. Okay, we don't really need 10 to the minus 9. Small is enough. Okay, but it's a small number, that's what I did. Right? To argue that this number is small. Now, if you look at Nu and Nu bar, right? Nu, we can write, okay, this calculation we did earlier. If you change variable from k to u, which is t times t nu times u, right? K equal to t nu times u. Okay? Then this can be seen as proportional to t nu cube times some function of mu nu over t nu. Clear? From here? And N nu bar is t nu cube times same function of minus mu nu over t. Okay, this function has no small or large parameter, right? Arguments may be small or large, but this function is just a regular integral. So N nu minus N nu bar over N gamma. N gamma goes as t cube, right? Some constant times t cube. So this goes as t nu cube over t cube. Okay, up to some additional factors, so numerical factors, times constant, times f mu nu over t nu minus f minus mu nu over t nu. Is clear? This is of order 1. T nu over t whole cube is of order 1, right? Some 4 over 11 factor. So if this number has to be extremely small, 10 to the minus 9, and if f is a regular function, the only way this can happen is if the arguments coincide, right? Or they are very close, the arguments, which basically means that mu nu must be close to 0, or mu nu over t nu must be close to 0. Right? Otherwise it cannot be small, right? This number being small, 10 to the minus 9, can be achieved by making mu nu over t nu small of order 10 to the minus 9. Then the difference will be like f prime of 0 times mu nu over t nu, right? Which you can think of as 10 to the minus 9. So this is approximately f prime of 0 times 2 mu nu over t nu, right? And you can check that f prime of 0 is a perfectly finite number. Okay, so mu nu over t nu becomes of order 10 to the minus 9. Something like that. Is that clear? Okay, so this shows that this implies that mu nu over t nu is small. Okay, and you can set it equal to 0 for all practical purposes. Okay, unless you want accuracy to 1 in 10 to the 9, you can set mu nu over t nu to 0.
Please repeat this part. How can we make this number so small?
see, we have f of x minus f of minus x, right? We know that this difference is small. Right? So the one way to make this difference small, in fact the only way to make this difference small, because f of x you can show is a monotone function, okay, is to make the argument close to 0. Right? Because then the two arguments almost coincide and then the difference is small. Right? So that's the reason why mu nu over t nu has to be small. Right? Because this is x, this is minus x, right? The arguments can coincide only if x is very small. Is this clear? Now, if you go to the electrons, here, as long as the electrons are relativistic, the temperature is above the electron mass, the same argument will apply there. So after all, Ne minus minus Ne plus is very small. Okay? 10 to the minus over n gamma is 10 to the minus 9. Okay? So again, you can see the difference between these two, right? For Ne minus and Ne plus, what is the difference? One has mu e, another has minus mu e. Right? So how can you make it small? You make mu e small, right? Or mu e over t small. But this argument breaks down at a temperature much smaller than Ne. Right? So let's try to see how that happens. Right? Why does it break down at a temperature much smaller than Ne?
So like we saw for the proton that mu p had to reach MP.
Exactly. Right? So here also, at sufficiently low temperature, right, mu e has to reach MP. Okay? Just for the protons, mu p had to reach MP. Right? We saw that if we had kept mu p to be, even though NP minus NP bar over n gamma, we know is very small. Right? But nevertheless, we saw that when the temperature comes down sufficiently low, right, we cannot keep mu p to be 0, right? That will not be able to balance the equation, right? We have to take mu p approach MP. Okay? Similarly, here you will see for sufficiently low temperature, mu has to approach Ne. But the question we will try to determine is how low a temperature it has to be for mu to approach Ne. Right? Because that will tell us whether we have to take into account or not. Right? Because we will see on from the other side that we have to go down to certain temperature before the nuclei form. Okay? So you have to compare the two and then decide whether we need to take into account this time dependence of mu or not. Is this clear what we are doing? Then you have to check when does mu have to become time dependent. Right? Mu cannot remain, mu over t cannot remain small all through. Right? Just like mu p over t couldn't remain small all through. Right? But you have to see at what temperature that happens. Okay? So that you can see whether it becomes important or not. So I'm going to erase this. Okay. So first of all, we have already argued that for t larger than me there is no problem, right? For t larger than me, it's like relativistic. So mu over t has to remain small, right? In order that Ne plus minus Ne minus over n gamma is small. So t much less than me is for the region we are considering. So when t is small compared to me, we use non-relativistic approximation. Okay, what does it mean non-relativistic approximation? Basically, we write square root of k square plus me square as me plus k square over 2me. Okay, that's what we did for the protons. We substitute and we get same formula that we wrote yesterday. All you have done is that you have replaced MP by ME. Yeah, because now we are talking, consider the electrons to be non-negatively stable. N gamma, on the other hand, is AB times T cube. Right? And AB, I think, was what? Pi square over 50, just some numerical constant. It's some constant of order 1. So if you calculate Ne minus Ne plus over N gamma, this gives you 2 over AB, AB over 2 pi t to the power 3 by 2 times e to the power minus AB over t, and then we have basically I think 2 sine hyperbolic AB over t. Because the e to the minus ME over t is a common factor between Ne minus and Ne plus. And then the difference is, in one case you have e to the plus mu over t, in the other case you have e to the minus mu over t. Okay, that's what gives you this sine hyperbolic. Okay, so now let's state the problem again. So you see, what we like, this we know is of order 10 to the minus 9. Okay. So what we will expect is that this means that this mu over t must be small, because that's what we are adjusting to make satisfy this equation, right? Because I have only mu over t goes as mu over t for small mu over t, right? So 10 to the minus 9 there means mu over t must be 10 to the minus 9. The problem, however, is that when t becomes much smaller than ME, this number starts decreasing rapidly, right? And if this becomes less than 10 to the minus 9, then you are in trouble, right? Then we have to now increase mu, right, to compensate, because this is fixed, 10 to the minus 9, right? It can either go above or below 10 to the minus 9, right? Now, if this becomes less than 10 to the minus 9, you have to compensate for it by making mu over t large. Is that clear? So, you have to try to see at what temperature does this happen. So, if you ignore the numerical factors, basically, we have to see is ME over t to the 3/2 times e to the minus ME over t when this becomes of order 10 to the minus 9, then mu will start moving. Then mu over t begins to move, begins to become large. Okay, and basically it begins to become large, and mu comes close enough to ME, so that the exponential damping here gets compensated by the exponential growth of the sine hyperbolic from here. So I just calculated some numbers. So if we take t equal to ME over 20, then this number over here is order 10 to the minus 7. You are still okay. It has not become small enough for the mu over t to become big. Okay? So if this is 10 to the minus 7, right? That means what? That this is 10 to the minus 9, here you have a factor of 10 to the minus 7, right? we can manage it by taking mu e over T of order 10 to minus 2. Okay, but it's still small. So at me over 25, me over 25, okay, this number becomes order 10 to the minus 9. That's when you have to start, mu over T has to start moving, okay, start differing from 0 appreciably. Okay. Pardon? Yes. Mu over T should be of order 1, right? After that, mu over T has to increase, right? And basically mu over T has to approach, mu has to approach me, right? Or close to me, so that the decrease in this is compensated by the increase in this. This temperature is of order 0.02. This is 0.5, right? 0.5 or 0.25, so that's our 0.02 electron volt. Right? So the temperature comes down around that time. We have to start taking into account the effect of non-zero mu, right? Above the temperature, we can just set mu equal to 0, or mu over T equal to 0. And we'll see later that the nuclear formation happens at a temperature of order 0.1 electron volt, roughly 0.1 electron volt. At 0.1 electron volt, right? That's 0.1 electron volt means that's me over T, right? Me is 0.5, right? So me over T is order 5. Order 5, this approximation is good enough. But me over T of order 5, right? This number is not very small, right? So you can think of mu over T as very small.
So AE is 0.5 MeV.
Pardon?
AE.
0.5, sorry, all of these are MeV, not electron. So 0.1 MeV is when the nuclei will form. So up to that point, okay, that's up to that point is why you have to do this evolution, right? Because after that, right, once the nuclei form, the neutrons get bound. So then there's no decay, right? There's no evolution of the number densities anymore. Okay, everything is stable and this number gets frozen. Okay. So we'll study that process in detail next time. Okay. That how do the nuclei form, right, by analyzing the dx and dt. But this is just to show why we can proceed from now on thinking of mu e and mu nu both being 0. Okay, in all the subsequent analysis, so instead of having to solve coupled equation, right, we just see an ordinary differential equation dx and dt equal to some function of xn and t. T is known as a function of time. T and t nu are already known as a function of time, and mu e and mu nu we just set equal to 0 in subsequent analysis. Is this okay? Okay, so next time then we'll give the result for this evolution of dx and dt, right? What you get xn as a function of time. Yes. Exactly. Up to this temperature, 0.02 MeV, or down to 0.02 MeV, right? But what I'm saying is the interesting physics question that we'll be asking, right, will all occur above that temperature. Okay. So because of that, okay, for that part of the analysis, we can just take mu to be 0.
Up to that. But after the temperature comes down,
Mm-hmm.
so then the nucleons will form.
Yes.
Okay.
Then you don't have to use that equation anymore, right? Because that equation was based on just free neutrons and protons, right? The conversion rate between neutrons and protons. Right? Once the nuclei form, right, of course things will change, right? For example, the fact that the neutron decays, right, that was one of the processes that we considered, right? That process is no longer relevant, right? Because neutrons inside a nucleus doesn't decay. Right? Helium is perfectly stable, right? And it has neutrons. Okay. So once the nuclei form, then you don't use these evolution equations anymore. Okay, and that will happen before this temperature. Okay? That's the main point. Okay? And that's the reason why in this part of the analysis we never have to worry about non-zero mu and mu.